All right, super busy day today, so let's see if we can crack another problem under 40 minutes, hopefully faster. So we'll see. Uh, this is, so this stream is for entertainment purposes only, and let's see what's the coding problem we've got today. Right, uh, pick one. Oh, oh no. Binary tree maximum pass sum. It's a hard problem, but many people like it. So let's see if we can do anything about it. Okay, so binary tree maximum pass sum. A pass in the binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them, obviously. A node can only appear in the sequence at most once, so no loops. Note that the pass does not need to pass through the root. Obviously, the pass sum of a pass is the sum of the nodes values in the pass. Given the root of a binary tree, return the maximum pass sum of any pass. So there can be negative edges too. Ooh, geez. All right. So So technically, when we're talking about the shortest pass, right? The pass with the minimum length, we're usually talking about Dijkstra if they're positive weights, and the Bellman-Ford sort of label correction algorithm when there are no such things. So the Bellman-Ford algorithm in this case, like if we will continue, so it's quadratic first of all, right? So we run through all edges over and over again in most v minus 1 times, where v is the number of nodes in the binary tree. And as a result, we have an extra label, let's say, on the tree node or something like that, or we have a map that tracks the weight of the tree node, so the maximum pass with which it can be achieved, right? But again, this is for arbitrary graphs. And again, under arbitrary graphs, if loop-free are prohibited, well, to be frank, if loop-free are prohibited, then immediately two things comes in mind. So let's go to the whiteboard. So first thing, right? So let's see this example too, which is actually very interesting. Let's go to the whiteboard and draw it there. So oops, what had happened? All right. So So because the weights can be negatives, all right, we really want to okay, so because the weights can be negatives, I'm not quite sure if 20, 15, 7, right? Well, the straightforward way, because we know that finding a pass in a binary tree will take uh, at most linear time, and basically all we can do is just go through all possible source destinations, which are not the same node, right? And see, okay, find the path between these two, if at all, if it's possible to reach, but because it's binary tree, so every nodes are connected there. And then just find the maximum. In this case, our time complexity, because number of nodes, right? So we have these edges here. So algorithm alg1 for each source destination, do, let's say DFS or BFS, doesn't really matter. Do DFS. DFS is n, source to destination is n square, final complexity is n cube to find the maximum pass. Uh, but because we have roughly 10,000, 30,000 nodes in the tree, given the conditions, constraints, it's more like we're looking for n square-ish. And then can we do Bellman-Ford here? I just wonder. So Bellman-Ford is for the given source destination, or at least for the given source, right? But source can be any, and destination can be any, right? So there should be something that tells us 100% that something is not needed to be searched. Let's say in this example, right, we definitely know that we most likely don't want to go through this because sum of these gives -1. So it's better just to have this pass. So it's like cover set problem or something like that, right? So basically what we can do is for each edge, so we shift from node to edge, we calculate its sum, right? So, and in this case, it will be, let's say, -1. In this case, it will be 10. In this case, it will be 35. And in this case, it will be 27. So the point is, yes, 10. So the point is that if we sort edges if we then sort these edges based on this weight, right, which is basically weight to pair of source of the two nodes, we may see that Um, so let's say sort edges, right? So I'm looking more like spanning tree plus some modification of it. So let's say 1520 will be the first one, then 2070, 27, the second one, then minus 1020. And 10 minus 10. So yeah, it's a hard one. What can I say? Well, we have this algorithm at least, right? Which most likely not feasible, and they want us really to find quadratic one. Or at least maybe n square log n or something like that. Um, so, okay. So, but okay, let's see the node itself. So in this case, we know that if we go here, we're getting 7 points. If we go here, right, we're getting minus 10 points. Does it make sense for us to go this way? Maybe it does if I have, let's say, this node 100 here, right? So in this case, I can go 50, 20, minus 10, 900. So local solution doesn't tell me. So there's no way based on one node or whatever I can tell if it's possible or not to achieve this. So what else do I know? Well, I know all weights of all nodes, right? At the beginning. So I definitely know the maximum upper bound on the pass. So does it give us something? Oh, it's not clear. The thing is, of nodes where each pair of edges and nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. But definitely, at least what I see, it makes sense to consider these pairs, right? Which I'm talking about as edges. And then from there, we know, okay, we can combine these one. We can combine these ones. So we start building paths. And the condition for combining, if we combine it and the sum improves, the overall sum, then we combine them. If not, we don't do this. So it's sort of like a merge of pairs. So we start with pairs, obviously, right? And then, so this can be done in linear time. So we go through all things. So we know the prior node value, the current node value, and we add it to some sort of map or something like this, like pair to the value or whatever. Or we can have a tuple. Or do we need a tuple? So the problem No, we need the 2, 3 nodes because we need to check if at least one of them can be connected to another one. So we can quickly check if 3 node equals left or right. All right. So okay, algorithm 2 is in ON steps, create pairs, because we definitely know that there should be pairs, right? And then for every pair, but this is again n square. But can we do something smart? Like saying that, okay, so for every pair we do like a merge, right? Sort. So maybe we can do n log n at least. Merge sort like. So we kind of split 2 pairs and see if we can combine them or not. I know the problem is it will be the weird structure, I would say. So what if we start from the maximum one, but again, no guarantees it will be the maximum pass. So yeah, I don't know. I mean, technically, to merge all of these and find the pass with the maximum sum, I mean, for this part, right, it's still O(n) squared. Ah, right. This is O(n) squared. This is exactly how we will do it. So for this one, we will look through this, see what can be merged, if it improves the sum or not, right? So right, we go and merge, then we choose the next one and you can go and merge wherever possible. Go to the next one, go and merge wherever possible. Then we merged all of them. If something was already part of the pass, we will find this as the maximum one. I guess this will be the right one. So let's see how to implement it properly. Okay, we're roughly 15 minutes into this problem. So let's switch to the default scene and let's see if we can do something here. All right. So let's not have a pair. Let's have a set such that we can merge 2 sets together if needed. If more nodes can be added there, right? So it will keep the set of nodes with each other and so forth. All right. First step. Map pairs to sum. Recursively. So Just basically nothing. Map pairs. Right, we start with some node, next, and then we have unordered map of what of unordered set, right? Of 3 node. To to integer, which is the sum. All right. Path to sum. Obviously, what do we know is that the minimum length of the path is these 2 nodes included, right? So we use this should we say using path to sum equal this thing, so we do not bother ourselves. Path to sum, and this is what this is, let's say reference. So what do we do is, so initially we don't bother ourselves with combining things, right? We just say, okay, this is the pair, so nodes can duplicate each other in between themselves. So we start with all paths to with all one hop paths basically. Put all one hop path in map. That's what we do. So the root here and this. All right. Let's also add this thing here. Next. Then what do we do here? Right. So basically we say unordered set of 3 node, right? That's what we have. One, or say left pass, let's say left pass, and same thing as you may guess, right pass, right? Right pass. So we say pass to sum. It's a little bit too early. But basically, there will be left pass equal to something. Left pass equal to something, right? Let's say 0 for now. And right pass equal to something, let's say 0 for now. And then we call map pairs what? next left pass to sum and right pass to sum. So initially, all we need to check if obviously next equals now PTR, then return. We do nothing at all. We just stop here. So left pass, insert. No, this isn't like this. So it's basically this thing. So if next left not equal now PTR, then we do this thing, right? So the only thing we need to check initially that the root is not now. Insert next, insert next left, and here is next value plus next left value. All right. Then same thing as you may guess, but for right one. Right. And oops, seems like forget something. Weird, whatever. Although I think it should be something like this at least. All right, so we have right pass. So to the right pass, we insert same thing, but for the right child, not left one. And the sum is basically this thing. All right, but now right. Interesting, whatever. And then we say right pass to sum. All right. So the only thing we check, basically if we check, let's see, just immediately, if root no PTR, I don't know, return 0, right? So we don't bother ourselves. So if it's not, then we do something. Then we say, so once we've done this, right? If there is no one hop pass, So there is no adjacent node. So technically there is no pass with the maximum value. So if pass to some size or just empty, so we don't bother ourselves. Return what? Return return 0. So now merge one hop pass if their sum is increasing, right? So or maybe even non-decreasing, right? So the logic for non-decreasing is that, let's say we add some subpass, so we combine two paths, so the overall sum remains the same, but these may allow us to add more to our original path such that the overall sum will improve on the next iteration. But if it decreases, but then it may increase. Yes, let's only do increasing. Or, yeah, let's do non-decreasing. So, but then if that path leads to better paths, then at some point we will merge these two, then their sum will improve, and then we say, oh, now if we merge them, it's actually not decreasing, but increasing or non-decreasing, so we can merge them safely. All right. How to merge in OR and square, right? So this in the map in OR n. So this is the simplest part. Now we need to merge somehow. So all right. The problem also that the pass itself, maybe we took the wrong structure, right? Maybe we want really the list so we can access it from the back or from the front and then add from the back or from the front. So it's not the set. Let's make it a list. List, right? Let's Google CPP linked list. Let's just see how it works. I know maybe double linked list, so it doesn't really matter. So we know the head and the CPP list access first element so I'm looking for the structure that gives us O1 of accessing the last element and the first element. So that's what I'm looking for. So the queue accesses the first element, I guess, in O1 and the last element. Um, first, last, access first, last element, constant time. So maybe it's double linked list. In this case, it's, I don't know, list front. Mm-hmm. And then how do we, I guess merging two lists is also easier. You just concatenate them, right? Why it's so, why it's never easy to find something in fast. It's always examples. Well, I can do array theoretically, but then it will slow us down when we will merge them, right? It will, um, let me see, double linked list. Yeah, I don't know. Whatever, let's just keep it simple. Let's just keep it list and then Google if we can do something. CPP list example. At least we can do front, back, right, and then list. First, second, third, fourth, blah, blah, blah. So list, fifth, says off. All right. Um, How much time? Oh, geez, we almost run out of time. List of 3 node. Oops. It's here, I guess. List 3 node. And then how do we add element there? Is it push, insert, or? All right. First, last. Cool. Heck, let's figure out it. Or just keep it whatever. Like this, it's just 2 elements, so it doesn't really matter. And then just return also 0. Let's just say if it compiles. I don't think it's insert. I think it's push or something like that. Some int seriously? Implicitly deleted? All right, let's just not bother ourselves. Maybe this one is a mistake. Never remember syntax. All right, because we don't know what the heck is this, right? There are code to implicitly delete a default constructor. It should be this, yeah, right? We cannot even need the map. The heck. Why it's so complicated? It should be straightforward. They say you have to return this, merge, whatever. All right, so we're running out of time and we did nothing, but that's okay because we nailed the algorithm. It's just stupid education part. Despite I'm tired, I just wonder if we can do this. So really don't understand why it doesn't want to compile here. Implicitly delete default constructor. The heck is this? It's because of vector, another map of vector or something. There is no hash. There is no hash for this one. But do we really need a map? If we anyway will go through this, right? So let's just, we don't care about the map basically. We don't need the map. We can just basically make it vector of whatever, maybe. Do we want to do this? So if we merge stuff, let's do vector. Who cares? But then it will say that we need a pair of this thing. So it was right. So using pass to sum is this thing. And then we can say pass to sum. So they don't have hash for the map. Interesting. Yeah, but we don't need map technically. We just need to keep pairs, and list of pairs is also, vector of pairs is also fine. Vector of pair of list. Gosh. So we do the same here. So then we don't need to do this. We can just pass to sum, push back, left pass. Here is make pair, right, left pass, and the value. And do the same here. And then we go to the next one, right? All right, should work. Yes, so it's not insert. I guess it's push or something. Push and push and push and push. Seriously, is push back? Why don't you say how I can range constructor? Those are constructors, parameters, take races, blah, blah, blah. How to add element there? So these, so they show examples with no adding element. Right, CPP, add element to list. Insert, push back. So what the heck? Insert didn't work, so let me see. Just push back, whatever. Push back. No, come on, are you serious? All right, so at least we compiled something under 40 minutes. No, actually over 40 minutes, but whatever. Now, what do we do with this? So we have 2-1 and 2-3 lists. Obviously, all we need is to go for every list, and until the size of this list won't change, right? Or vector won't change, we don't stop. All right, so let's see, while something the only part I'm worried is the merge, because merge will be somewhat, yeah, it will screw the complexity. We need to have a good data structure for this, maybe pass or something like that, where we have front element, back element, and then we have something in the middle. Ah, so technically, we don't need the vector of things. We need always the pair of things, because we don't care about elements in the middle, right? We only care about the head and the tail of the pass. So let me see if instead of list, I will also do a pair here. Pair 3 node and 3 node. Should we do tuple? Pair of pair is stupid. Tuple. CPP tuple example. How to make simple tuple of 3 elements. Let's see. make tuple. Yeah, I think we just say tuple, number of elements there. So just this thing. So we have vector of tuples. No, we still need this. All right. So how do we add it there? So all we say when we push back make tuple, and now we don't need even this thing. We just say next tuple. Next and next left, next left, and the sum, right? That's it. Okay, this is how it should work theoretically. All right, make tuple. Next right. Yeah, we don't need pass here now. It's even easier. We don't need these things. It's even easier. Next right, and then the sum of next value, right value, left value. All right. All right. So now it's interesting. So because we don't care about the elements, we need to return the sum. We don't need to find the path itself. Or alternatively, you know, so this niche, so we can find it in linear time after all. All right. So let me check if the code's still running. Oh, yes, it won't run. So let me see. When 40 minutes turned into 120 minutes. But that's okay. All right. So let's say int last size equals 0, and while or let's say last size is pass some size plus 1, and then we say pass some size last size minus pass some size, because there is should reduce not equal 0, and initially it will be 1. So we do the cycle. So what do? We basically now merging if two pairs combined, creating a not decreasing pass. And how do we check if there is a pass? If the left element equals to the left or to the right element of the second pair, or vice versa, or the right element equals to this. So, right? Then, so it's simple cycle for int I equals 0, I less than. Let me see. So we create the new vector, right? So basically for every, I think it still will be on cube in this case. Something smarter should be done. So we go, let's say we pick the first one hop pass and go through the rest of these and combine whatever possible, right? Then we do the second pass and combine whatever pass. Then we do the third, combine whatever possible, fourth, and so. The problem with this approach is that it's still in cube. It's still in cube. So I think the idea is right, but the problem is how to combine now. How to merge the pass. I don't really think it can be only done in an n cube time. I don't think so. Or maybe it will be n cube log n time actually, because while cycle here, it won't go through till only one is left, right? And pass to some size greater than 1. Empty, return 0 if pass to some size equals 1, return pass to some, I don't know, front, doesn't really matter. And then how to access element of the top. It's std get student 0, student 1, whatever. So we have a tuple. And we can do structure binding. Tuple I think it's just std get to, that's what it is. All right, works. I mean, not the code itself, but the way we return things. Let me make it clearly. So now, so for every element in I, which is I less than what, then pass to num size, right? I plus plus. We do another cycle. And because they're symmetrical, what I mean is if we check I and J passes, like if we can merge them, we don't need to check J and I. So we can start with J equals to I plus 1, right? And let's see. So this is J. And J plus plus. And obviously we don't need to go through the last element, we need to go through the last minus 1. All right, so what do we do here? Well, we do simple thing. We access out, let's say, if we can do this, I like this decouplings thing. I guess oriented as a function, whatever. So we can just say auto, right? We can say source. We can say destination, or source I, destination I, value. And what do we say here? Well, we say pass to sum I. So and then we also do the same thing for the J, right? So the only problem now is that the rising element from the vector won't be an easy thing. If you copy stuff and move them around, I wonder if we won't just create every time we go here the new pass to sum, and then pass to new pass to sum, and then just at the end of the side of this thing, just repush it, so we don't need to worry about it, right? New pass to sum. So this is J now, right? All we do, oh gosh, it's already 1 hour past. Menu crack. Our problem under 40 minutes. Nope, never. So if source I equals source J, or source I equals destination J, or source I equals destination J, source Right. So then it will be destination I equals source j, or destination I equals destination j, right? So if they are connected, basically, that's what we're asking for. Can form the pass. If can form a pass, then we say what? Then new pass, then we check another if, or we can actually add condition there, right? We can say, okay, this thing if can form a non-decreasing, so this is while I and while j, non-decreasing pass, and while I is strictly less than while I plus while j, right? So this way we guarantee that we can merge them, basically. That's what we're saying. So now we need to push, sorry, how it's called, new pass to sum, push back. Now we need to decide on the source, all right? So we know that at least one, either source I or destination I, is matching. So if we say if source I this, and really I shouldn't do this, I should just use it for separate source, destination, and then value. If either source equal to j or I, right? Otherwise source I. If it's equal to one of these, then what would be the source? The source will be element which is, it will be in another condition. So source equal to j, all right? If yes, then its destination j becomes the new source. Otherwise, it's source j and source I. You see, now we have constant time of merging things. It's cool, but super unreadable, super unreadable. Damn. All right. Let me see if I can do at least like this. It's terribly written code, but it's better to have auto whatever here reference and then just assign which one it will be. But we're doing this way. I think it's also fine. All right. Now we do the same thing for the destination I. Oh. Oh ho ho ho. Well, if source is matching to one thing, right? All right, we say it's source here, source I. If it's not matching to anything, it remains source I, so then the destination should be updated. Same for destination I. If destination I is matches to something, all right, then destination I needs to be updated. If not, then it's destination I. Then its source would be matching. So one of these, either this will be true or this will be true. If this is true, then we update the source. If this is true, then we update the destination, but we won't update both, basically, right? Yeah, it's unlikely. It shouldn't be the case, but let's see if the logic works here. If destination I equals, let's for symmetry say destination J, then we say source J, otherwise destination J. So if we wire them at the destination, then we put source, right? And the value actually is tricky to see. All right. Because it's already one node in this value, right? So technically, value j here should be, let's say, int val additional value is what? Oh, let's do this. Okay, let's do for simplicity this thing first. Right, so we stop here. We don't do and thing. We just stop here and whatever. Let's pull while I so far. So we know that. All right. So this is if, and this will be another if. While I is less something, and then we have this additional value. How do we compute it? It's basically while j minus, and then we need to find which thing is this. And it's basically exactly the same thing here again. Additional value equals, well, j. Now we say, let's do this, if source I equals source j, then additional value minus equal what? Destination j, sorry, source j value, right? That's basically, so if we merge this as the source, then from value j, we should subtract value of source j. So it's a straightforward if. And obviously one of them will work, only one of them. The destination j, then we do destination, if destination I equals source j. Oh, all right. If source I equals source j, or destination I equals source j, then additional value, we subtract source value, right? And else, and we can use else here because we definitely know that at least one of these is equal. Else, we just say basically this, right? Additional value destination j value. Got it. And now we say if while I is strictly less than while I plus additional value, right? It's basically if we can form a non-decreasing path here, if two subpaths can form a path, right? A non-decreasing path, and this is the check that if value I is strictly less than value I plus additional value, right? And I guess we don't need this. Then we do this, source I equals source J, or destination J, yes. Then source I equals source J, yes. Then destination J is our source now. If not, then source J is our source. If this is false, then our source remains source I. Similarly for destination, if destination I equals to source J or destination I equals to destination J, then we need to change our destination in the pair, right? So then additional value here. And if destination I is destination J, right, then our destination becomes the source of the J. If not, vice versa, destination J or destination I, obviously. Right, so now we merge this. And this, ladies and gentlemen, is merge in O1. So now we merge in O1, but every time we merge, the number of entries at best shrinks by half. In the worst case, it remains the same. But if it remains the same, what do? We do nothing because, right? So then what do? After this for cycle, or sorry, did I miss something? Oh, okay. Right. If for it's another if of this thing, then we have this thing, and then we have this thing, and then we have cycle while, right? Right. So finally, what do? Finally, we say that last size is equal to pass to num size, right? And pass to sum, sorry, equals to new pass to sum. Oops. Once this is done, all we need is basically int value equals to 0, and then we do for. We can use it to const auto because we don't care anymore. Right, and then we say source destination value, and we say pass to sum, and we say max value equals max, and max value and value done this or and return max value. Jesus. Did we crack it or not? Push back is not working. Interesting. But it works here. Oh, because it should be make tuple. Yes, we should also move this thing here. All right. Run the code. Memory will be super terrible. But it works, hey! But will it work everywhere? Nope. Uh-huh. So, stupid check, but true. So if um, if passed to some empty and it's not now PTR, then we should return root, right? Value. It's not the pass if you have one node. That's what you said. You can have one node as a pass. Whatever. But can you have just one node as a pass? It actually a little bit changes the conditions because I started with the pairs, right? And damn, always tricky conditions. Hate it. Submit. Most likely to go somewhere else because it will say, oh, there is a node with super huge number output one expected to exactly. That's what I'm saying now. Or actually, it can be very easy to fix. And then what we do, then we have another basically queue or something to iterate through all the nodes we have. It doesn't really matter. We basically traverse the entire tree and find the maximum value of the node and then compare maximum value to the max node value and return the maximum. Int max node value. And by the way, the max value here, based on the description, should be minus 1001. Similarly here. Right. So, actually, it can be very straightforward. It should be just int. All right, max node value. Max node value, and all we say is tree next. All right, that's all we need. If now ptr return minus 1001. All right. Then again, we can say if just next equal now ptr, we do nothing, right? We return minus else, or just this. Then we return max. Let me see, cpp max of three numbers. Is there anything simpler than just doing Oh, all right. Nice. That's what we do. We say next while, and then max node val, next left, left, and max node value, right. All right. So let me see where we want to break it, maybe here. And then all we need is to say this return, we don't need this, return max, between max value and max node value. So this is another linear complexity, unfortunately. Run the code. Let's see if it still works. If nothing is nothing breaks, and see if now we pass this stupid test. Oh, but why? I don't understand. So output one because let's see. I got it why it happens because it finds one pass here, right? And we say here we go, nothing to do. That's why. Root value. Return, oh, we can do again the same thing. Max this and geez, and whatever max node root. Yeah, code is not beautiful, but who cares? Seriously, why? It should work, but it doesn't. All right, let's see. Int max, sorry, oops, node value equals to this thing, right? Let me see. What do we return? Cout max node val equal max node minus 1001. How come? So it literally thinks that this is greater than what? Than the value of 2? It's weird. Super weird. Oh, of course. Oh man. Gosh, it's already like double the time limit. Expected 4. pass. Let's see, from source val to comma destination val value equals to value. Let's see what's wrong with that. Feels like we're almost done. We technically nailed it. It's just time to debug it and see where we screwed. Pass from 3 to -2. Value 2? Damn it. All right, let me see. First of all, same thing here, just to make sure. Before we do anything here, let's just see what's going on. All right. So there should be 2 pass, not 1, 2. So we have pass 1 minus 2, value -1, and we have pass 1, 3, value 4, right? And we also have pass 3 minus 2. No, we don't have such pass. No, sorry, it's after the merge. So the problem is we did merge from 3 to -2 through the 1, but why did we do that? So this is 4. All right. So, and this is -1. Oh, because we can improve -1, that's why. So then we need to make it symmetrical. So we need also to check if it benefits the second pass, right? Otherwise, it doesn't make any sense. So all we need to do is for additional value j, let's say, and we can do oh, wait a second. We already know I did, right? So we don't need this. So we know the additional value, right? This is the sum of 2. So what we need to add and value j is less than what? Than uh, uh, so this will be, well, I minus additional value will be the what we add to the value of j from the I side, right? In this case, we won't merge them, right? Let's see if this is the case, and we should be done. I really shouldn't do that because it's already way past time limit, so it's just stupid. But sometimes the problem is interesting and you just want to solve it no matter what. All right, we have 1, 2, 3. Interesting. It works here, but it doesn't work here. How come? Oh, we do not merge them now. Why is that? We do not merge them because of this, right? Think. Ah, so we don't need last size, or we do. Um, so basically what we want to say that if pass to sum, a new pass to sum empty, right, we break. So we were unable to merge anything. So, uh-huh. So do we really need last size or whatever in this case? I don't think so, right? So all we need is this. So once we have one pass, nothing to do. Or if we can really reduce them, that's what we do. Submit. Wrong answer, wrong answer, wrong answer. Dumbass. So, okay. So we have pass 1 to 2, value 3. Pass 1 to 3, it's value 4. Right. So now pass 1 to 2, 1 to 3, again, string 4. So we do not merge it for some reason. But first of all, why don't we merge it? Just curious. Right, so value I is 3, value j is 4, right? And we know that the common node is 1, so the additional value is whatever, 3, right? So we say that if 3 is less than 3 plus 3, which is 6, yes. And 4 is less than 4 plus 3 minus 3. So something wrong here. So additional value in this case, right? When we compute it for 4, right, it will be what? We subtract 1, it's 3. It's 3, right? Should it be val j here? Yeah, it should be val j. Right. Submit. Oh gosh. What breaks? Say time limit exceeded, so I can go home. No, just wrong answer. There are nulls in the middle. So we have pass minus 10 to 20, which is 10. Wait a second. Minus 10 to 9, which is minus 1. 10 to 20 is 10. 20 to 15, all right, which is 35. And 20 to 7, which is 27. So next time we merge minus 10 to 7, because we had 20 to 7 and minus 10 to 20, right? And it was 10 And this one was 35. Interesting. Output 52, expected 42. So we need something better here. I guess here. But it's really the last one to check. So, oh gosh, going for the record, 2 hours of solving stupid hard problem. No energy drink. So, okay, I will clear the frame for myself and we'll do debugging part. So we have minus 10 to 9 and minus 10 pass to 20. All right, we say this value of 10, this value of minus 1, then they also have another two paths, which is 20 to 15 and 20 to 7. And the sum is 35 and 27. All right, now what's left? So then we merge minus 10 and 7 and minus 10 and 15. They all have the same value? Super weird. I mean, how come on earth they have the same value? So if we merge this pass is 37. No. It will be output 52. I don't even understand how we get there. And how do we get to 42 in this case? So we definitely don't go through minus 10. So we start 10, 15. No, I mean, it feels like the largest pass is really joining 15 and 7. So it will give you what? It will give you yes, it's 42. Yeah, I know, but why it's 52? I didn't get it. It shouldn't really improve the pass. That's the problem, right? So the problem is how I calculate this value, really. So the additional value, the value j minus additional value is the value of this common node. And what I'm saying is right. So for val j, I actually add val of I minus this thing. That's what I'm doing. All right. So then if I open the brackets, value of j and value of j will cancel out each other. So it will be val I plus additional value. Yeah, so the value actually of these two will be the same, but then you just need to check that it works for both, right? So that's why. Submit. Did I? I not even want to accept these stupid answers. Time limit exceeded. Finally, we were unable to crack it. But we did all we could just to get, what, 19 tests out of 94. So it's still too slow. It's still too slow, although this is a constant time we're making here for merging pass every time, right? We're merging pass, and every time we merge in it, we shrink array. So it's n squared log n technically, because theoretically every time we half it. Although in the worst case we may not actually half it, by reduce it by 1. So in this case it's n cube, and in cube it was trivial, yes. And there should be an n squared solution, I guess, right? And let me guess, it will be super trivial. Pre-order traversal Python bit 67. Recursive easy solution. Oh, you can just solve it recursively. Who could have imagined that? So max e, max root, well, max e. Left plus right plus root max e. And child max plus root 12 max e. Root, All right, so actually it's sort of traversal only. Basically from every node, I guess. Damn, I thought really we can beat it, but maybe not this time. All right. So let's go to the whiteboard and finish this miserable day. And what one more time was the submissions? 19 out of 94. All right, thanks everyone. Have a good one.